at Unesp, the same university you are now, but in another campus in Rio Claro. And he has a master and PhD degree, also in computer science, and both from Universidade de São Paulo, located in São Carlos. So we have some friends here that came from there, right? And he did a sandwich period in United Kingdom, in the universities of Surrey and Kent. Nowadays, a professor at Universidade Federal de São Carlos, we call UFSCar, for those who don't know. And he did a period of postdoc at Porto in Portugal before the pandemic. His research concerns bio-inspired algorithms, such as artificial neural networks and evolutionary algorithms, and also machine learning, with particular emphasis in multi-output learning problems and machine learning for data streams. We can say Ricardo is bio-inspired in his research in computer science, and I'm sure this inspiration also helps to understand a lot biology as well, and from another perspective. So help me to welcome Ricardo, who will be here for 3 days.
Okay, thank you very much for the introduction. Hello, everybody. So we are talking about a little bit about machine learning. I don't know how many of you are familiar with machine learning. So we are going to talk about some algorithms in machine learning that you can use into your biological data, okay? Who knows what machine learning is? Let me know. More or less, okay? Someone can tell me what's machine learning? Mm-hmm. You can say, what is machine learning?
Yeah, I think machine learning is a class of algorithms. Except the other microphone. This one's better. So it's a class of algorithms where you can, by giving examples, make this kind of algorithm be able to either classify or output data just by somehow training it with examples or things like that.
Yes, exactly. So you can learn from data, okay? You can learn to perform a given task when using some kind of data, many data. It can be labeled data or not, okay? This data can have labels or not. Okay, we're going to see here. No, where is it? The presentation is not here, sorry. Mm-hmm. Okay, thank you.
But do you want it like fully?
Yeah, fully. Nice. So the first thing we are going to see that learns from data is a little review on linear regression and multiple linear regression, okay? So I'm going to give a review to you about what's linear regression, then we are going to perform some code, both in linear regression, then multiple linear regression, then we are going to work with some shrinkage methods where you can use the linear regression to select features. So this is very useful in many biological cases, biological data where you want to select features, okay? Yeah, okay. Where is that pointer here? So the first thing we are going to remember is what is a simple linear regression, okay? So it's a method that we use to predict a quantitative output, let's say y, based on a single predictor variable, okay, x. So we have to assume there is a linear or approximately linear relationship between variables, see? And then we are going to find this relationship. So we are going to seek for 2 beta values, okay? So this is the true coefficients. If we have, for example, if we had the whole population of data, we would know the coefficients that lead to a linear relationship between the variables. Okay, so these coefficients represent the intercept and slope in terms of the linear model. I mean, that will be a line, okay? Intercepting the points. But the thing is that we don't know these coefficients, so we have to estimate these coefficients based on a sample, because we don't know the whole population, okay? And so, see, these guys are unknown. So we must use data, as he said, to estimate some coefficients. So then suppose we have this kind of data, okay, x, y, x, y. So we want to obtain the estimated coefficients, okay? What have I done? Oh, that's my computer ran out of battery. That's my fault now, sorry. No. Yeah, but just give him 1 minute, it will turn on again. Yeah, we are. Yeah. Oh, I'm just going back to the slides I was. Yeah. Okay, so sorry for that. Okay, so suppose we have these data points. Okay, so we want to obtain estimated coefficients that are as close as possible from the true coefficients, okay, that approximated the population, okay? So we want to find an intercept and the slope. You know the intercept is the point where the line crosses the y-axis, and this beta 1 is the slope, okay? So we want to find these coefficients based on data. So, yeah. So how do we estimate these coefficients? What we need to do is to minimize the least squares criterion, okay? So this is the least squares criterion help us to measure how close our line, which is the result of the estimated coefficients, is close to the original line, okay? So we are going to consider this the prediction for a measurement of y based on a given value I of x. Okay? And we know that given a predicted value for our outcome, okay, we can, and the true value of our outcome, we can compute an error, okay, which is the desired outcome minus the predicted outcome. So this error represents what we call the residual for the I error, okay? So it's the difference between the IS observed value and the predicted value, okay, by the linear model. So this is performed to evaluate the linear model, okay? So the residual sum of squares is calculated by this formula, okay? This means that we are going to get the error for each outcome, okay, square it and sum, right? No. Question?
So, Professor, I always think the linear model normalizate the data. Is right to think like
No,
this?
you don't have to normalize the data, okay? You just have to suppose that there is a relationship, a linear relationship, approximately linear relationship between the variables, but you don't have to normalize the data, right? Okay. This is not working. Oh, okay. I came to the... So how do we calculate the estimated beta? So we use this formula. Okay, with this, we calculated the estimated beta 1, and with this, the estimated beta 0. So this is a sum over each observed point minus the mean of the points multiplied by the observed outcome, the true observed outcome. Okay, remember that this is supervised learning in machine learning, so we have the desired outcome, so we can calculate its mean, divided by the sum, okay, again, the observed outcome minus the mean, okay? Okay, having this beta 1, we can simply calculate beta 0, okay, easily. So with this, okay, this is the least squares, and with this, we estimate a line, okay, that represents a relationship between y and x. Okay, nice. So, see, as I said, beta 0 and beta 1, okay, this is the fit of the model, okay, and is found by minimizing the residual sum of squares. Okay, so that calculation minimizes the residual sum of squares, okay, for a given data. So what we have here are the points, okay, the points of our sample, the red points, and these gray lines, okay, are the errors between the induced line, induced model, and the true points of my sample, okay? So what we have to find is this line here. And how do we evaluate our model? I mean, how do we evaluate our estimated coefficients? So how close are the estimated coefficients, okay, from the true values of the coefficients? Okay, we can evaluate by computing the standard errors associated to each coefficient, okay? So the standard errors are calculated by this way, okay? Where this parameter here, okay, is the variance of the error. Okay, so this E contains the errors for each observation. So, given the model, if you have our model, okay, we can predict some Y values. We compared the predicted values with the desired response. Then we can compute the errors. With the errors, okay, we can calculate the standard errors obtained or related to each of the coefficients. Okay, so this gives us how close are the estimated coefficients from the true coefficients. Okay, and see here we are working with only one predictor variable, only one x. Okay, but this can be extrapolated to work with more than one variable. So that will be multiple linear regression. Okay. Questions up to here?
Okay, I don't believe I actually got like the idea of how close are the beta 0 and the beta 1 to the real values, because we can have like a square data like which fits like square parameters, and like the data won't actually fit a regression model. And in this case, what are we saying, like how close are to the true values?
Okay, but if the data doesn't fit a regression, what do you mean? If there isn't a linear relationship between the data, then you cannot fit a linear regression model. Okay, you will never find these correct coefficients because there is no linear relationship between your data. So it depends the data you have that I can say it's most of the data. In most of the real data, you don't have linear relationships between the variables. So you have to use other kinds of models. Okay, so in this case, it works. In other cases, it won't work. We are going to see other algorithms like decision trees, okay, where you can have a no linear relationship between the variables. Then we are going to see how the decision tree splits the feature space, okay, because each x here is a feature of a given sample, a given example in my data. So we are going to see how these models, they separate, okay, the feature space in order to classify data or in order to predict a numeric value for a given data. Okay?
In the last part, when you say the variance of the errors, you mean the residuals variance, right? Okay.
Yeah, it's a residuals, yeah. Yeah, good question. These are the residuals, okay? The errors between the observed outcome and the desired outcome. Okay. And with this, we can also compute confidence intervals for our errors, okay? And for our coefficients, okay? So, for example, we can compute a 95 confidence interval, okay, where I can say, okay, there's a 9% of chance that the true value of my coefficient falls in the interval, okay, that's given by the coefficient that I just estimated. You know, so we can calculate that. That's very easy to calculate, okay? So given the linear regression, we just get our estimated coefficient, okay? And add 2 times the standard error that we just calculated before, right? C here, okay? So what this tells me, there's a 95% chance that the value that I just computed fall in this interval, okay? So this interval There's a 9% chance that it will contain the true value for the estimated beta. Okay, and in the same way I can compute the estimated beta 0, the estimated interval for beta 0. Okay, and finally we can evaluate our model. Okay, we can estimate the standard deviation error, what mean we call it the residual standard error of our model. I mean, getting the difference between the computed, the estimated y, and the true y. So what we are doing here is that getting the average error, okay? We are getting the difference between each observation and the prediction, okay? Squaring, take the root, and with this we can evaluate our model. So we expect that this value will be very low for good models and high for bad models. So the lower this value, the best is our model, okay? Let's put this in some codes. Are you familiar with R? Yes? No? More or less? Okay. So I'll do this with you. Okay, should I increase the letter? Yes. I think you already have this, don't you? I sent it to Guy. I talked to Guy, and okay, this is very initial, but we are going to get into more funny models, okay? Okay, guys, so if you look at this, okay, we know, okay, that this y equals beta 0 plus beta x plus an error. That's a population regression line, because we don't know, of course, the true, we don't know the true population, so we don't know these guys, okay? So what we actually can compute is this formula, okay? This regression line, this least squares line, okay? Beta hat and beta 1 hat, beta 0 hat, beta 1 hat. Okay, we can compute this because that's based on a sample from the population. Okay, in machine learning, we know that we'll never have the entire population. If we have the entire population, we can fit the perfect model. We never know. We'll never have that. We have some sample of the population, then we can fit a model. This model must be able to generalize to new data. Okay, so what we are going to do here, we are going to create 100 random values, okay? So what I'm doing here is just, see, I'm getting 100 here. Then I'm running, what I'm doing here is to sample some numbers from a uniform distribution with the minimum number is -2, the maximum number is 2. Here and here, I have the numbers. Okay, so this is going to be our population, okay? And now I'm going to generate an error. Okay, just to spread our points in the space x. Okay. So I'm going to define an error here. This is a vector, okay, from a normal distribution for 100 numbers with mean 0 and standard deviation 1. Ooh. Here, these are my error values. Nice. So, given my error values, what I'm going to do here is generate 100 corresponding y's. Here. These are my y's. Okay. Are you following? Okay. Yeah, you can open it in a browser. Is it okay? Nice. Okay, just now I just computed the y, the corresponding y's. And now I can plot data. So this is my data. So you see there is a linear relationship between x and y. That's why it is possible to fit a linear model. Okay. So here, what we are going to do, we are going to calculate the values for beta hat and beta 0 hat and beta 1 hat. Okay. So here, this is the same formula we saw on our slides. So we are going to get the sum, see here, of a value minus the mean of the sample times the outcome, the true outcome, minus the mean of the true outcome, and we are going to sum that. And then we are going to divide by the sum of the squared value of x minus the mean of x. And we are going to return it. So this is a function I'm defining here, okay? So beta 1 here is a function that gets as parameters the x and y. Okay. And I'm doing the same thing with beta 0. It's a function that receives as argument x, y, beta 1, and calculates here beta 0. Okay, and now I'm just calling the functions. See, I'm first calculating beta 1, then I'm passing beta 1 as argument to beta 0, and calculating the values here. Beta 1, beta 0. So these are, let me print, I think it's easier. Here. So I have the values for beta 1 and beta 0. Okay. With this, okay, now we can draw the true relationship line and our least squares line. Okay. So we have here, you see, we have the true values of beta 0 and beta 1. They are here, okay? What I'm doing here is that I'm getting a y value given the true values of beta. Then I'm going to plot this. Okay, I'm going to plot the data, then calculate up here the values based on the true relationship. Okay, and then here I'm going to plot the true line. It's easy if I do that. See? So the red line here, okay, is the true line. And the black line is the least squares line. Okay? Did you get it? Because here I'm getting with an error. I'm getting y with an error and getting the coefficients corresponding to the y I just get. Okay, and here I'm not inserting the error and computing, okay, the linear regression without error. So there is no error related to my y. So with this I can get the correct true linear regression line. Okay, and the black line is the least squares line that I just showed in the slides how to compute. Okay. So, but how close, beta 0 are from beta 0 hat and beta 1 hat are from the true values of beta 0 and beta 1, okay? So what I'm going to do here is to compute the least square line again and get the standard errors related to beta 0 hat, okay, related here to beta, okay? And then standard errors for beta 1. So what I'm going to do here, okay, is the same thing, it's just the same thing we saw on the slides. I'm just getting the standard error related to each value of beta I just calculated, okay? So here, see, to calculate the standard error related to beta 0, I have a function here where I receive here, okay, as hyperparameters x, y, and the error, and I just computing here the standard error related to beta 0. Okay, I'm getting the variance of the error, okay. This error is the difference between y, the true y, and the predicted y. And I'm multiplying here by 1 divided by the number of points I have in my sample plus the means here divided by the sum, okay? The same calculation we saw in the slides. And I'm going to do the same here. Oh, sorry, I have to compute this. And I'm going to do the same here for beta 1. I'm just execute here. So these are standard errors, okay? This tells me how close, okay, are the true betas from the the predicted betas, okay? See, let me show you. Because you know that the least squares line we calculate without the errors, okay, is 2 and 3, right? The true coefficients, 2 and 3, see? So the calculated ones are, see, 296 and 198. So the standard errors are telling us the difference between the values, okay? So instead of 3 and 2, we obtained 2.96 and 1.98. So the differences are here. Okay? And we can calculate the error related to our model. See? That's the sum of the error. Okay, the squared sum of the error divided by the size of our sample. Actually, what I'm doing here is computing the length of our sample minus 2, because that's the number of degree of freedoms, I can say, okay? N minus 2 is the degree of freedoms of my error. So this is the error of my sample. Question?
Yeah, I have a question about the standard error. In the formula that you showed in the slides, the sum is not squared, and here we have it squared. Why? Like
It's not.
the whole parenthesis there, the mean of x squared over the sum of the...
Okay, let's see. The standard error here. Oh no, because it's the same, right? I just squared both sides and I get standard error here and square here. Root square both sides, you know?
Yeah. Yeah, okay, I think it makes sense. But like in the code, the only thing that's squared is the summatory, I think.
No, the square is in everything. See? No, it's okay, good question. And you see, okay, I just evaluated the model, and just for you to see, okay, I just get the error here, okay. I squared the error, okay, divided by the length of the sample, and then calculated the root square. So what I'm going to do here, I'm going to get, okay, see, the y given the error, the y without the error, okay, and then I'm going to do the same calculation here, and again get the same value, just to show you that the calculations are the same, okay. Y minus yp. Yeah, and here are the confidence intervals, you know. Just execute here. I have here the confidence intervals related to each coefficient. So there is a 9%. There's a 9% chance of that the true value of beta will fall in this interval. Okay, this interval from beta 1 and this interval from beta 0. Okay, now let's get the same data and do some R implementations, just to see that our calculations are almost the same as the implementation in R. Okay, maybe there are some difference because of decimals, decimal points, you know, some rounding some numbers. There are some difference between the numbers because of the calculations, but you are going to see that the values are more or less the same. Okay. So getting y, see, we are going to fit a linear model. And I'm almost sure you already saw this in the course, okay? So we're just fitting a linear model here. See, and I'm getting if you see the intercept and the slope, these are almost the same values we obtained with our calculations. Okay, so what I wanted to show here is how to calculate by hand what's going on behind the formula, okay? Here. And here it's a summary. So we can see here the standard errors related to each of the betas, okay? And here, that's a p-value associated with the standard error. So there's a really good chance, because the p-value is very low, okay, that our predicted beta will fall in the interval of given by that interval we just calculated, okay? Okay, and here I'm just showing the intercepts, are the same ones that are here, okay? Yes, and here are the coefficient intervals. They are more or less the same we just calculated. Okay. And then we can produce predictions given a new value. Okay, with the predict function, okay, we can know what I'm doing here. I'm just getting a new number, a new x. So I'm just sampling a number, well, which between the interval -1 and -2 and 2, okay? And then I'm getting our model and using it to predict the value of this new data. Okay? Here, this is the value of our new data. And yeah, the value of y given our new data and x new here. If I get x new, that's 0.33. So given this x, the predicted value is 299, okay? And again, we can plot the data we just fitted. Oh, I have to click here. So this is the data. That's very similar to the data we just plotted. Okay, is it okay? Do you have some questions? So you know now how the linear model works, okay? Now when you are executing the LM in R, you know what's happening behind the function. Though the function is performing these calculations we just calculated here. Questions? Okay, now let's continue. Yes. With multiple linear regression. Okay. What if now we have data that has more than one variable, x1, x2, okay, xp, okay? So the analysis we just performed can be extended in order to accommodate these additional predictor variables, okay? So what we do is that we give, okay, we associate to each of the variables, okay, a different slope. That's a different beta. So here, you know, this is just simple linear regression. So we just extended for more variables, okay? So X represents the given predictor, and we have a beta that quantifies the association of that predictor, okay, with the response variable that we want, y. Okay. So given the estimated betas, okay, so with this formula that's very similar to the simple linear regression, we can estimate the outcome. We can estimate the desired outcome. Then we are going again to compare the desired outcome with the predicted outcome to get the error for the model, okay? So the parameters here, okay, are estimated using the same least square approach. We use it for linear regression, but we are going to have a more complex matrix model, okay? And then the error of our estimated model is calculated just, again, by the same form, computing the difference between the desired response and the predicted response, squaring it, summing. Okay, remember that for each true response, we have the predicted response. Okay, that's given by all the model. Okay, so the predicted response corresponding to yi is our whole multiple linear model. Okay, corresponding to xy. See? So the sample y has p variables. And there is a linear relationship between the variables and the response. Okay. So unlike the simple linear regression, now we have multiple coefficients, okay? So we have complicated forms that are most easily represented using matrix algebra, but we are not going to calculate this. We are going to use R to calculate this for us. Okay. And what we do now is that we have a given hyperplane that represents the linear relationship between the variables and the response. And we want to minimize the difference between the points and the estimated least squares plane, in this case aqui, because here we have a three-dimensional space, x1, x2, and our outcome. So the least squares will minimize the distance between the desired points and the plane that estimates these points. But we can have more than one here, x variables, xp variables. Then we are going to have a given hyperplane that fits into the points. Okay? Nice. So let's do this in R again. Ooh. Yeah, here. Well, in order to fit a multiple linear regression, okay, we are going to use some data. But before that, we are going to work a little bit with some data. Okay, you have this load and analyze. Yeah, you don't have the file. How can I send the file to you? No. Yeah, I can send to someone, then. Just give me an email. Yes. Let me just confirm, yeah. Lucas. Okay, I just sent to you. Now I'm going to wait till you get the data. Chegou o e-mail? Yeah, just the data. Are you with the data? Is it okay? Okay. So if we just read this data, okay, like here, you are going to see that this is a small part of a data set where you have, where each sample, for each sample, the features of each sample are SNPs, okay? Single polymorphism nucleotide. Who knows what it is? Okay, it's a small mutation related to one nucleotide in the DNA. Okay, so each feature of our sample is a SNP. And at the end, we have a desired numeric outcome. It doesn't mean what it is. Okay, it can be the production or some of the production of a given, I don't know, quality of rice, you know. It doesn't matter. So what we want to do here, we want to, given the SNPs, predict, let's say, the productivity of some product. So, okay, but let's take a look at some variables, okay? So I'm taking a look here at SNP data, here at variable 6, okay? So see, we have the most of the values are A, the other values are C, okay? What I'm going to do here is to verify which of the data are not complete. I'm going to check here what are the samples that have missing data. Why am I doing this? Because I cannot work with data with missing values, okay? So there are different things I have to do here. The first thing I'm going to do is to input missing data, okay? And then I'll have to convert this data set to a numeric version because I cannot work with categorical data in the linear regression. How am I going to multiply a categorical value by a number, okay? So, if I have missing data, okay, I must fill the values, for example, with the mode. So I'm going to do is to fill the missing values with the mode of a given variable. Okay. If the variable was numeric, I could fill the missing values, for example, with the mean or the median value, okay? But as I am working with categorical variables, I'm going to replace the missing data with the SNP value that appears the most for that variable, okay? Of course, this is just an example. I'm working with a biological data. Maybe there is some biological related technique to replace a given nucleotide with other nucleotides, but I don't know that. I'm just going to use the mode, okay? Just for example purposes. So what I'm going to do, for example, let's get the F. F, what's F? Let's see. F is are the values for the variable SNP4. So what I'm going to do, I'm going to get see, these are a factor, see, you know R? So this is a factor variable, okay? The levels are A and J. So what I'm going to do is to get the argument that maximizes the number of levels, okay? See, A is the value that most appear here, see? If I get the variable, SNP4, see, that are 408A, 51G. So I'm just getting which one is the max. Okay, the max is 1, the first position. And I'm just getting the levels in the first position. It's A. Okay. Very good. With knowing that, what I'm going to do, I'm going to get, for example, given SNP4, I'm going to get for SNP4, the lines where SNP4 is missing. And I'm going to fill these lines with the values that appear the most for SNP4. Did you get it? Okay. See, now there are no more missing values for SNP4. I just replaced everybody that was missing with A. Okay, now I'm going to make a function here that does this for me automatically. Okay, I called it the mode. So mode is a function that gets a variable x and check if this variable is a factor. If it is a factor, it just returns what I just have done for snip4, with snip4, okay? If it is not a factor, I just transform it in a factor and do the same thing. So now I have this function mode, and what I'm going to do here, just for you to understand, for example, if I get snip data in line 3, okay, snip data in line 3, it will give me all the columns, all the columns related to line 3. You see that there are some snips and there are some missing values for line 3. So I'm going to do what? I'm going to get the positions, okay? I'm going to check what positions are not available. This returns me a vector of true and false, okay? True related to where snip data in line 3 is not available, false otherwise. Now here I'm get what are the positions that are not available in snip data in line 3. So these columns have data that are not available. And now, with this line of code here, I just get the lines, you know, the examples that have missing data. So what I'm going to do here is that I can use the function applied to do the following. Hey R, get the function mode, okay, and apply to each column, to here is refers to column, and apply to each column where there is missing data, okay, in the line 3. So it's going to apply this function to all the variables that are missing here in line 3. But I not just want line 3, I want all the lines. So I'm going to do a for loop here. Okay, for all the lines that have missing data, I'm going to apply the function mode to these lines. Okay, so here I just performed everything. Okay, and now if I check if there are complete cases, if there are missing cases here in SNP data, there are no more missing cases. Okay? Okay, good. Now what I'm going to do is to save this version of our data set here. I'm saving here. I have this path here, but you can set the path you desire, okay? So I'm saving this data to data snips, no missing. And here I have my, okay, I have my data saved. Now we need to one-hot encode our variables. Okay, do you know what one-hot encoding is? Okay, one-hot encoding, I'm going to explain here. Now, suppose I have a variable here, SNP1, then I have another variable, SNP2, okay? And here I have the, I'm not putting X, sample1, oops, and I know, sample2, okay? So this snip has value T here and value A here. This snip, I don't know, has value G here and value C here. So the one-hot encoding does the following, okay? I get the number of values for each variable and transforms each variable in another, in n variables, where n is the number of values of the given variable. So for example, SNP1 will be transformed in SNP1A and SNP1T. Okay, SNP2 will be transformed in SNP2G and SNP2C. Now, the sample S1 has the value T for SNP1. So I'm going to put 0 here and 1 here. Okay, the sample 1 has value G for the variable SNP2. So I'm going to put 1 here and 0 here. Now if I get if I get sample 2, it's going to be 1 here and 0 here. And for SNP2, it's going to be 0 here and 1 here. Did you get it? From transforming the variables, okay?
But do you have to generate a column for each possible value?
Yes, you generate a column for each possible value.
Okay.
That's exactly. Of course, we can, for example, suppose I had another value here. I don't know, S3, I don't know, add another value G, okay? I can still use 2 columns because I can say that if it's 0, 1, then it's T. If it's 1, 0, then it's A. If it's 0, 0, then it's G. You know? It's not necessary to use a 30 column for the 30 value of the variable, because I know that if this sample has 0 for 2 values, then of course it has a 30 value. No, then I just use a codification with 2 bits, Yeah, so this is also possible. Let me just, okay. Good. So to do the one hot encoding, you are going to need these 2 packages. Okay, I already have them installed, so I'm not going to install them again. So I'm going to just load them here, okay? Just load these variables. I mean, there are many packages that have this function one hot, okay? I'm just using this one here from the caret and ML2's package. So this one hot is a function from the ML2's package, okay? For it to work, I have to get my SNP data and pass through this function here as data table, because it only works in this format, okay? See, one hotting. Now I have that format I just showed you. But we can also use these dummy vars, okay? So dummy vars, I'm saying the following. I'll get a dummy variable here, okay? I'm just constructing here this dummy using dummy vars. And I am saying that I'm going to apply it for all variables, okay? And the data that I'm going to use is SNP data. Then I'm getting this, receipt that I just constructed, and we will use the function predict to apply this receipt to a new data that it's the data that I want to convert to one hot encoding. And now I have this new data that's SNP data here. And it's the same format as before, okay? These are 2 different functions that perform exactly the same thing. Okay, so I have here a one-hotted version of our data set. And now I'm going to save a version of this data set. That's data SNPs, no missing, dummy. Okay, it is saved. Now with this, now we are going to go to the multiple linear regression and perform the multilinear regression with this data, okay? Very good. So multiple linear regression, okay? So let's load our data. We just constructed this data. Is everybody following? Is okay? Is it executing? Okay. Okay. Now I have the data I just built. Now here I'm going to fit a model using all variables. Okay, so I have my target, that's the numeric variable. Okay, and I'm saying to this function that I'm going to fit a model using all the predictor variables against the target. Okay, and the data I'm going to use is this SNP data I just loaded here. Okay, see? Now I have all these coefficient values. However, see, there is a warning message. 50 not defined because of singularities. What does that mean? Sorry. That means we have high correlated variables that can be unnecessary in order to fit our model. So we have to find where these correlations are and remove these variables, okay? And that's what we are going to do here. So, sorry. So for example, if I get here, like SNP1G, SNP1T, okay, these are two variables. What can we see here? Yeah, one is exactly the opposite of the other. Like when one is 0, the other is 1, and vice versa, okay? So we can infer the one from the other. Like if I have a sample and SNP1G, I know my data, right? So if SNP1G is 1, okay, so the value of the variable is G. But if it's 0, it's T. I don't need another variable just to say that, okay, the value is T. I just check if it's 1 is T, or I mean, if it's 1 is G, if it's 0 is T. Okay, so let's remove one of them, one of these variables. So we are going to remove highly correlated features from the data set, okay? And I'm going to use here the Pearson correlation coefficient, okay? For this to work, I'm using this function core here, passing as argument the SNP data. Good. Then I'll have the base correlation between all variables. So if I execute here, what can I say? So in the diagonal of the matrix, all the values are 1, of course, because one variable is highly correlated to itself. But I have some cases where I have a highly negative correlation, okay? So here's the one that we just saw, okay? SNP1G with SNP1T. So let's remove this case, because we don't need them. They're unnecessary. Oh, here I have the whole matrix, okay. So what I'm going to do here is count the number of extreme correlations, okay? I'm going to see how many extreme correlations there are in the data set. By extreme correlations, I mean correlations that have a very high value, above 0.999, okay? So I'm getting the upper tree part of the matrix, because this is a triangular matrix, so the part above the diagonal is the same as below the diagonal. So I'm getting the upper part of the matrix, okay, and checking if they are higher than 0.999. So I'm going to have a big vector of true and false. Then I am sum all the values, and if I apply sum in a vector with true and false, it's going to sum all the positions that are true. And then I have that here I have 50 extreme correlated values. Okay. Our original data set had 50 variables, 50. 5 plus 10, 50, okay? When I applied the one hot encoded, it turned it to 100, because each variable had 2 values, 2 possible nucleotides. So now I'm going to remove 50 of them, okay? If I get the summary of the correlations here, I see that the minimum correlation I have is -1. Okay, this is a very high correlation. So what we are going to do, from this library caret, we are going to use this function find correlation, okay, to find the correlations that are above 0.8, okay. So I'm getting here the columns of the matrix, where the correlations are above 0.8, okay. See that are all the, I have 50 values here, you know, because for each variable, I have another one that's highly correlated with it, okay. So what I'm going to do here is remove the columns with correlated variables. So I'm just getting my SNP data and indexing it with the highly correlated variables, and I am removing the highly correlated variables. So I now have SNP data filtered. If I compute the correlation matrix again, we are going to see that our new correlation matrix now doesn't have those highly correlated variables anymore. Okay. So if I see again the highest correlation value, you are going to see that I don't have those highly correlated variables anymore. So I'm going to use this new data to fit my multiple linear regression again. So I'm using the same command here, the same line of code, okay? I'm getting the target, and I'm saying, okay, get all the variables as predictor variables against the target, using the data we just filtered. And now we don't have that problem anymore. Okay? So these are the estimated coefficients, okay? You see that it's interesting that we never compare the standard error for, the standard error we compare. But we never fit, what's the meaning of beta 0, you know? Yeah, it's intercept, but what does it mean? What does that mean? What happens if I have all the variables equal to 0 except beta 0? All the coefficients equal to 0 except beta 0.
If all the other betas are zero, it means that the variables are not significant to the model?
No, sorry, I didn't get it.
If the coefficients are zero, it means that...
Yeah, if all the coefficients are 0 except beta 0.
That those variables are not really significant to the model?
Yes, and what does that mean?
That they're not explaining your model and you should look for other variables?
It would be the same as predicting the mean of the sample. Okay?
Oh, yeah.
It would be the same as predicting the mean of the sample. Okay? So here I have all the coefficients. Nice. Now we can make predictions with these new coefficients. Okay? So I get The same data I use it to fit the model, and here a parenthesis. Okay, I should never do that. Okay, when evaluating one model against the other. So suppose I'm going to see, I want to see what is the best model for a given task. I should never use the training data to compare the models. I should always use test data because I want to see how my model is going to generalize using new data. Yeah.
There's one of us at home, and he said, like, why do we need to remove the highly correlated lines? Does that can negatively affect our prediction, or is a way to store less data?
I don't understand. Oh, sorry.
I know, he said, why do we need to remove the highly correlated lines? That's the first question.
Yeah, we need to remove them because they are going to be unnecessary for our model. That's the main response, okay? Because they are variables that do exactly the same. The explanation that they give to our model are exactly the same.
Okay, but my question is why we do not just remove one of them?
But we removed
because we removed the pairs.
No, remove it just one. We remove it just one.
We remove just one of each pair.
Yeah.
Okay, sorry.
How does R decides which one of the pairs to remove?
Yeah, it doesn't matter. Actually, it doesn't matter because yeah, we could use some heuristics. For example, get each variable individually. You see which best explains the model. I mean, get the lowest error individually without using the others. Fitting a single linear model using just that variable, see what one's the best. But in practice, we can remove, any one of them.
I understand the reason behind removing one of those because they are equal, but letting the two in the data set wouldn't make our model more robust? And then
not necessarily, no, because they do, if you get the variables, they are, exactly highly correlated. Suppose, let's think about a numeric variable, okay? One is growing like the other one is exactly the same growing. Or when one is like growing, the other is decreasing, but exactly in the opposite direction. Yeah. So they explain exactly the same thing in the data set.
Yeah, I understand.
So if we leave them, we can have actually a different, what's the word? We can have a different the result is that we can have a model with a higher variance. We are going to have much more variables, then the model is going to be much more complex, then the variance of the model is going to be much higher. We are going to see what's bias and variance, okay? If the variance of the model is high, the model will actually memorize data. It will not be able to generalize with new data.
Mm-hmm. But like in this specific situation, I understand because we have like the same number of correlation and non-correlation. We have 1,000 variables, and then half of them it's equal one to another. But like if we have something like 30 variables, and then just 4 are highly correlated, like it do not means that we need to take this more in account than the other variables, because if then we have 4 that are highly correlated, then we take the just one, and then this one will have the same importance as the all 26 others, but it isn't real because it has the importance of other 4. You got it?
Yeah, but what we do is to remove the 3, get the more important, and leave the remaining 26, they remain the model.
Yeah, but
I don't remove them.
Yeah, but now this one that is representing other 4s will have the same importance that the other 26. But this is not real.
No, it's not going to have the same importance as the other 26.
Oh.
It's a separate variable, and it has a given importance. I don't know what this importance is. And the other 26, I also don't know what are their importances. I must discover that with the model.
Okay.
But I don't know if that one's more or less important than the other 26. I cannot say that. I cannot infer that. The only thing that I can infer is that, okay, these high correlated models, they contribute the same to explain the outcome. So I can remove one of them. That's the only thing I can conclude. Like, it's the same as when we do PCA. You know PCA?
Yep.
So when we do PCA, okay, we are getting the variables that most explain, like the principal components that most explain the data. And these principal components are combinations of the variables of my model. So what I'm doing, a transformation of the data and getting the data that explains more getting variables that explains more the data and throw the others away. Okay. Here I'm just throwing away the high correlated ones. Okay. So what I'm going to do here, I'm just, oh yes, sir.
I guess just on the technical side, when you again on this point of having correlated variables, right? I understand that there is something weird going on when you have correlated variables because there should be fewer degrees of freedom, basically, right? Like if y is a function of x, like alpha x, then you have the degrees of freedom, and then something should go wrong. But are complaints that there is a singularity. So I don't see where in the formula you can have like, do you divide by 0 at some point? Where does the actual problem come in? Because I understand that you shouldn't do it, but what goes mathematically wrong in doing it?
No, I think mathematically wrong, I don't see that you are going to get, no, I think mathematically it's not going to, it's not going to happen anything. I don't know exactly why the package gave me this outcome, saying there are singularities and it didn't compute the beta. I think here the package is not computing the beta because he's saying that it's going to be the same value, for example. Okay, the contribution will be the same, so it doesn't compute for a given variable. But mathematically, it's not going to happen. Okay? Because I'm just removing to decrease the variance of the model because I don't want a model. Why do I need a model with so many variables if I can just remove some of them that explain the outcome exactly the same way?
Yeah, it's because what LM says is like 50 not defined because of singularities. It's kind of a very strong thing to say. Yeah. But it's okay.
But these singularities are highly related, I mean, with the highly correlated variables. And, okay, now I'm going to predict some data. I'm getting the model I just induced, right? I'm getting some data here, and I'm going to predict the value for this data. So I'm getting a pred. And what I'm going to do here is to construct here a matrix where I'm going to concatenate the predictions with the true value. Okay, this gives me the true value. I'm getting my data, rows 1 to 10, and I'm getting the last column. Okay, the last column is a target. And here I have the prediction and the true value. Okay, it's not that, but it's okay. Okay, it's a very simple model, you know. Now what I'm going to do here, I'm going to do a more realistic experiment. Okay, so I'm getting my data set. I'm getting a seed here because with this seed, you all can get the same partitions. So I'm getting my data set, and I'm going to divide it in a train and test. In train and test data sets. So what I'm doing here is that I am sampling the numbers 1 and 2. Okay. And how many times? The number of examples in my data set. So suppose I have, I don't know, 500 examples in my data set. So I'm going to sample 500 ones and twos. It's like I have a bag with 1 and 2. There's only 1 and 2 there. So I put my hand in the bag and take a 1. Then I put a hand in my bag and take another number. And I do this, I don't know, 500 times. Okay? And every time I put my hand in the bag, there's a probability of 0.7 that I get a 1 and a probability of 0.3 that I get a 2. Then with this, I'm going to have a vector of 1s and 2s. Okay, there's 70% more 1s than 2s. Good. And now I'm going to index these values. So if I do this, if I ask what values are equal to 1, I'm going to get a vector of true and false. True are the positions where the vector is equal to 1s and false otherwise, okay? And then if I get this true and false vector and index my training data, it will return to me all the positions, all the rows where, all the rows corresponding to position true. Okay, if I index it with 2, it will return to me all the rows corresponding to the positions false. I mean, false, because then we are going to be true, okay? If I do this, it will invert. True will be false and false will be true. And with this, I get some training and test data. I'm randomly separating my data, okay? So I'm just going to execute this. See, this is the data frame I just got. Okay. This is the training data, okay? And these are the dimensions of the training and test data. Okay. So the training data has 378 samples and the test data 163 samples. Each data set has 51 variables, okay? 50 predictors and 1 target. And with this, I can fit our model, I can fit a linear model using the training data, okay? So I'm fitting, and once I fitted my model, I'm going to predict the values for the test data. So this is a more realistic machine learning experiment, okay? And see that I am removing the target to make the predictions. Then I'm combining the prediction with the true variable, the true outcome, the true value, okay? Column bind, I'm building a matrix. And here I'm just giving names to this matrix. So predicted values, true values, and printing the table. And here I have the predicted values and the true values, okay? So for some of them I have very near values. Nice. And I can compute the mean square error giving the true values and the predicted values. And here are different forms of computing the mean square error. You know, the mean square error, I can loop for each row of my table, compute the difference, and divide by the number of values. Or I can just get my matrix and see, get the matrix and apply this function here. Okay? In each row of tab 1, apply this function. In each row of tab 1. And then I sum everything and divide by the number of lines of table 1. I had the same value. Or I just can get the mean of subtracting each line, and squaring each value. It's the same value. Okay? Questions? Did you get it? Okay, so, yeah.
How do you know that your mean squared error is too big?
That's a
how
good
do we
question.
compare?
Yeah.
There's something to compare with?
Yeah, I mean, the lower the best. I mean, the lower the best. The closer to 0, the best. This is not a very good model because, I mean, I got here a sample, a small part of a big data set. I just got random variables. I really don't know if they truly explain my outcome, okay? I just got to show you how it works. And I really don't know. I think this is not a good model, okay? This is not a good model because it has some values that are very far from the true outcome. See here, for example. But for some cases, it has values that are very close. Here, for example, far, close, okay? But the rule is the lower the best, okay? And we can use this mean square error to compare models. I mean, if I had another predictor, then I can compare these different models and I can see which one's the best, okay? And now, after lunch, we are going to see shrinkage models. I mean, what if I want to know what are the most important variables to explain my model? Okay, then I can get some of these coefficients and penalize them and make it go towards 0. Okay, the closer to 0, the less important is the variable. So the closer the coefficients are to 0, the less important the variables. So again, we can throw away some of our variables and we can decrease variance, improve the model. We are going to do how to do that. Okay, yeah, I think it's time, right? No, okay.